Hi, welcome to Mathematics with Tom. This is Tom, and today I'd like to introduce the idea of probability. So that's what we're going to do. We're going to get an idea of probability and what it is. We'll start out by writing correctly. Probability. So what I've done here is I've already written down this data set. And this data set was created in 1940 by a mathematician named John Carrick. And Carrick was in Denmark at the time of the Nazi invasion, and he was captured and put into an internment camp. Well, while Carrick was there, Carrick actually flipped a coin 10,000 times and recorded the results. So this is the results of the first 100 flips, And this is how it works. He wrote down that the 0 is a tail, and the 1s represent the flip of a head. Okay. So this brings up our first thing that we wanted to notice. What Carrick was doing is Carrick was conducting a probability experiment. So let's write this. He was conducting a probability experiment. And let's give you a definition. And you kind of already know just by flipping a coin, a probability experiment is a chance process. With well-defined outcomes. Okay, well that might lead us to the next question, and that is a vocabulary word, probability experiment, that leads to another vocabulary experiment, outcomes. And the outcomes are the result of a probability experiment, Now, probability experiment. Well, look at this. When you flip a coin, there's two outcomes. And we've already addressed that. The outcomes, we know what they are. The coin can only be a head or a tail. That's it. So those are the outcomes. These are my outcomes of flipping a coin. Okay? If you're playing cards, well, you'd have 52 different outcomes because in a traditional deck of cards, there's 52 cards. So the experiment of just randomly drawing a card, there's 52 different outcomes that can happen there. Now, what I want to do is just using this simple set of data that Carrick generated for his probability experiment, I'd like to get an idea of this, and that is, what is the probability? Let me continue with my blue, and that is, what is the probability of a head, and I'm going to write it with a capital H. From now on, if I need to write heads, we'll just write it H. The probability of a head, or heads, was the probability of heads when flipping a coin. When flipping a coin. Okay, now we're assuming this is a fair coin. Carrick later did an experiment where he took a wooden coin, and on one side of the coin made a very thin lamination of lead. So let's just take a look. Now, we're going to do this in a very systematic way. Notice we haven't even defined probability yet. So what we're going to do is we are going to make a cumulative graph of the ratio of heads. The ratio of heads per, and we'll use these in per group of 10, per group of 10 flips. Now, we're going to use the 10 because it'd be too hard for us just to put a dot for every single one of these and keep track of the number of heads. So let's do this. I'm going to make a graph here. You could do the same. I would encourage you to do that. So let's see. I need a vertical axis. So I'll make my vertical axis maybe there. And let's make our horizontal axis like that. And we're going to start out, and we're going to go in groups of 10. So there's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So that's going to be our 10 groups of 10, or 100 individual flips. Okay? So there's 10, 100. We're going to go all the way up to the start. Now notice this. Let's look at our first group here. Our first group of 10. Now what I want to do is I want to find the ratio of heads. So at this point I flip the coin, and I'm going to keep my ratios. Let's keep track of our ratios of heads in this nice kind of pretty magenta color. So notice that in 10 flips I have 1, 2, 3, 4 heads. So the number of heads per flips is 4/10. So I'm going to add this on my graph. Let's go in tenths. I'm going to put this right here as 0.5, and that'll make sense, I think, as we go. And then I'm going to come down, maybe, oh, I didn't put that in a very good spot. Let me, So let's go like this. Maybe let's go 0.25. Now let's go here. We'll go this way. 0.1, 0.2, 3, 4, 0.5, and 0.6. So I'm going to extend my graph up a little bit. Here's my 0.5, 0.4. All right, so now look at what's happened. After 10 flips, my proportion of heads. So let's label this vertical axis here as proportion of heads. All right, so after 10 flips, my proportion is 0.4. Now, I'm going to just go a little bit just to show you this interesting. Notice that if I was to come down into this bottom and do 5, 4, 3, 2, 1, notice that this graph didn't even have one head until the fourth flip. So let's graph that. I'm going to put a dot right there at the fourth flip. And after 10 flips, we're up here at 0.4. Now, let's keep going. Let's see what we're at. So in this next group here, I pick up 1, 2, 3, 4, 5, 6 more heads. I pick up 6 more heads. Well, that's 6/10 there. That's 6 out of 10. But now if I add it, my total is 10 heads out of 20 flips. So I'm going to it's the 10 out of 20 that I want to record. So now when I'm at 20 flips, my proportion is right up here at 0.5, and so I'll put another dot. And now let's continue this. So for the next 10, I pick up 1, 2, 3, 4, 5, 6, 7 more. So that's going to be 17 out of 30 flips. 17 out of 30 flips. Now I've gone ahead and done a little bit of calculating for us. So let me pull that number up. So 17 out of 30 it's about 0.57. about 0.57. So that's going to be, here's 0.55, so 0.57 would be about there. So after 30 flips, now you don't have to do these dots, I just do them to help us visualize where the intersection of 30 flips and a ratio of 0.57 is. And then let's keep going. So for our next group of 10, we're going to add 1, 2, 3, 4 more heads. So that's going to be 21, 21, and we're now at 40 flips. Okay, so 21 over 40 is about 5.25. Well, oh, that's fit nicely right there. So let's come over here, go to 40 flips. You can see these are going to intersect right there. Okay, and let's continue. So in our next batch of 10, we're going to pick up 1, 2, 3, 4 more heads. 4 more, so we're at 25 heads out of 50 tosses. Well, that's 0.5. So let's go here. This is at 50 now. We're at 50 flips. 50, here's 70, 90. Need some of those to see. So if I come up here to 50 flips, I put a dot right there. Okay, we're halfway done, as a matter of fact. So now I have 1, 2, 3, 4. So now I'm at 29 out of 60 flips for that when I add that group of 10 into there. Well, 29 out of 60, that's going to be just a little tiny bit below the 0.5, and it's actually 0.483. So 0.483 is probably right there. Okay, and there's 60 flips. Okay, let's go to the next group of 10. So my next, my underscore. Okay, my next group of flips, this is going to put me up to 70 flips, And this is going to add 1, 2, 3 more for 32 total. 32 total, which is actually 0.45. 45, so this is going to be, it's right down above. So put a dot right there for 70. Okay, my next group of 10 here, it's going to put me up to 80 total flips, and it's going to add 1, 2, 3 more heads. So now I have 35 out of 80. 35 out of 80 is 0.4375, so right there. That's going to be probably right about there for 80. Okay, now we do this again. So now I'll have 90 flips total. And I add 1, 2, 3, 4, 5 more. That's 40 out of 90 flips, which is a repeating 4 if you stick that in your calculator. So that's going to put us just right below 0.45. And oh, here we are. We're at the end. Our last 10 flips for 100 total. And we're going to add 1, 2, 3, 4 more. So now we're at 44 out of 100. 44 out of 100. Which put it right there. Now, let's do this. Let's take this, and I'm going to use the green so it stands out. Notice we started down here, and not until the 4th flip did we even start to register. I'm going to connect my dots. Okay, and I'm going to do this. If you look at this, and if you just think about a coin, what you would expect is you kind of expect that half of the time you're going to be getting heads. And according to our graph, notice this, we're always just a little bit off, aren't we? I'll use maybe this nice orangish color here. Notice that we're a little bit below, and here we're a little bit above, and oh, look at this. On 2 different occasions, we were right on that on what we might expect when flipping a coin. So this idea of what we expect over time is called, this is called our limiting value. This is called our limiting value. And the fact that we're creating our limiting value by actually doing something, we would say that this is called our limiting value. Our limiting value is approached by empirical evidence, empirical data or evidence. What empirical data is data that's collected by observation. So that's what it is, empirical data, or in this case, empirical probability, is based on observation. It's based on observation. Meaning we flip a coin and we notice that as we keep doing it, we get closer and closer. And how close did we get, or how close did John Carrick get? Carrick, I believe. Carrick flipped the coin 10,000 times, of which 5,067 of those were heads. So Carrick found he had a limiting value of 0.5067. Pretty close to 0.5. Okay, that's the idea of what's happening. But what we do is we can never really prove the limit. We define the limit, and here's how we define it. So I'm going to go to another page, and let's see if our definition matches with that, or how that definition matches with our limiting value. Here we go. So I'm going to another page. Roll a die, just a single one. And this sometimes comes up, so people are worried, well, what kind of die? And we're talking about a standard 6-sided die. And I didn't know this for years, but those little dots on the die, so the 1 is represented by 1 dot. That dot is called a pip. So 2 pips for 2. There's 3 pips for the 3, and then opposite the 2 on the other side would be a 5 pips, and opposite the 3 would be the 4 pips. And in the very back of our cube that we can't see would be opposite the 1 would be the 6 pips. So when we roll a die, what I want to do now is we're going to write all possible outcomes. Write all possible outcomes. Okay, let's do that. So I could get a 1, I could get a 2, I could get a 3, a 4, a 5. I could also get a 6. I can't get a 0, and I can't get a 7. So when I write, these are all the different things that would happen when I conduct this probability experiment of rolling a die. And all possible outcomes, all the different things that could happen, this is called the sample space. Sample space is all possible outcomes. All possible outcomes. Okay, well, along that line, let's think about when we flipped the coin. When we flipped our coin, so we had a coin here, and we would flip it. Here's obviously the side for the heads. So we'd flip this coin, and it would go up into the air. Well, what could happen when we flipped a coin? Well, we could either pick up heads, we could get a head, or we could get a tail. So in this case, the sample space is just that. It's either a head or a tail. Now let's try writing one more sample space. And actually, before we do that, let's try this. So notice that the outcomes are 1 through 6. But let's say that I wasn't interested in only a single number. What if I was interested in for rolling the die, what if I was interested in rolling an even number? Oops, rolling an even number. Well, I'm going to write like this. I could do that by rolling a 2, a 4, or a 6. Well, when what you're interested in isn't just a single outcome, but a set of outcomes, we label it with an E, and the E stands for an event. And an event is a set of outcomes. A set of outcomes. All right. I think we're ready now. Let's try one more. And this time, I think we're going to need one more piece of paper to do this. So come with me. And what we're going to do is we are going to roll 2 dice. So the first thing I want to do is write the sample space. And I'm going to guide us how we do it. Write the sample space as the sum of the 2 dice. Okay. Now, there's a catch to this. We usually think of dice in a pretty pair, like maybe we got 2 red die, or we got 2 red dice, or we got 2 white dice. And when you're in Las Vegas, if you look, they always give you matching sets of dice. But when you're trying to figure probability, you need to look at it. You need to look at it a bit more creatively, and to actually see the whole sample space. Think of it not as 2 matching dice, but 2 different colored dice, so you can keep track of what each different die is doing. So I'm going to do this, and I'm going to have, we'll do a purple die here. Sure, we'll do a blue. Let's do a blue die. Here's my blue die. Okay, there's my blue one. And then let's also do, how about this purple colored die? So let's also have a purple colored die here. And maybe we'll have it on the 6. Okay, so let's record what could happen. Let's say you have a blue die and you roll it. Well, you could get a 1. You could get a 2. You could get a 3, a 4, a 5. You could even get a 6. Okay, now let's do this. Now let's roll our purple die. Well, if we do that, we could also get a 1, a 2, a 3, 4, 5. We could also get a 6. Now, we're going to record these results. As their sum. So I'm going to just put the sum over here. This is the mathematical symbol for the sum, capital sigma. So let's write these out. I'm going to use black. So a 1 plus a 1, that would be a 2. A 1 and a 2 would be a 3. A 1 and a 3, well, that would be 4, and so on. So 5, 6, and 7. And if we keep going, we'd have 3, 4, 5, 6, 7, 8. We'd have 4, 5, 6, 7, 8, 9. We would have 5, 6, 7, 8, 9, 10. We're almost done here. We have 6, 7, the 5 and 3, that's going to be an 8, a 9, a 10, 5 plus 6, that's 11. I had to grab an extra toe there because I ran out of fingers. Finally, okay, in the last row, we have 6 and 1 for 7. 6 and 2 is 8, 9, 10, 11, 6 and 6 for 12. This is how we see the sample space for rolling 2 dice. This is the sample space. Okay, now this brings up another point. If I ask for an 8, roll an 8, well, check this out. Let's do this in orange. Look at the 8s. Well, a blue 6 and a purple 2 is an 8. A blue 5 and a purple 3 is an 8. And look at this. There's 5 different 8s. So when we talk about an 8, rolling an 8, we're talking about an event. An event of 5 outcomes. Okay. I think we're now ready to find the probability of an event. Here we go. I'm going to define this for us. So, the probability of an event E, and sometimes you'll see it if it's an outcome, sometimes you'll see X used, but mostly you'll see an E. So the probability event is that it's the number of desired outcomes and then you divide that by you could say by the size of the sample space, or you could say the total possible outcomes. Those are the same thing. So we'll say the number of possible outcomes, which is the size of the sample space, possible outcomes. All right, so what do? Let's find these following probabilities. Let's find the probability. We're going to do a whole bunch. I'm going to write it this way. Make a little table. So I'm going to do an event. And then we're going to find the probability of that event. So let's do all of these. What's the probability of a 2? A 3, a 4, a 5, a 6, a 7, 8, a 9, a 10, an 11, and a 12. What about a 13? What about a 13? Well, the 13 can't even happen, so it would just be, it has a 0 probability. 0 probability means it just can't happen. Oh, let's write these now. So, how many ways can we get a 2? Well, here's a 2 right here. It's the only 2 there. So we would say that the probability of a 2 is 1. That's the number of desired outcomes. The total possible outcomes are all of these. If you count all of those up, how many are there? There's 36 possible outcomes. So the probability of a 2 is 1 out of 36. I'm going to write this as a fraction. And you'll see why. You can often write them as decimals, but fractions I think are easier to see where the numbers came from. All right, a 3. So look at this. The 3 that can happen 2 different ways, right there. So we'd say that the probability of a 3 is 2 out of 36. Now, I'm going to just come over here, and common practice is to reduce your fractions to lowest terms. So if I reduced 236, remember that's 2 times 1 over 2 times 18. So 236 is the same as writing 1 over 18. But for this example, and what you'll see in a moment, I'm going to leave them all with a denominator of 36. Let's continue these. So the probability of a 4, well, look at this. 1, 2, 3 fours. So I would say that the probability of a 4 is 3 out of 36. And continuing on, again, the probability of a 5, there's 1, 2, 3, 4 of those. So we would say the probability of a 5 is 4 out of 36. And continuing the 6s, there's 5 of those. And how about the 7s? 1, look at this. 1, 2, 3, 4, 5. There's 6 of those. 6 7s, so it would be 6 out of 36. And then the 8s, well, we've already seen that there's 5 of those, so that's 5 out of 36. And then if we look at the 9s, there's 1, 2, 3, 4 of the 9s, so we'd say that's 4 out of 36. And the 10s, well, there's 3. We can look over there and see there's 3 out of 36. The probability of an 11 is 2 out of 36. And the probability of a 12 is the same. It's the same as the probability of a 2. It's 1 out of 36. So what I want to do now is I'm going to sum up all of those events. Add them all up. Okay, this is going to be a lot to add here, so double check me. But here we go. So notice that since the denominators are all the same, all I have to do is add the numerators. So I'll start from the top. So I have a 1 plus 2 more is 3. Let's see. Plus 3 more, that's a 6. 6 plus 4 is 10. 10 plus 5 is 15. Plus 6 is 21. Plus 5 is 26. Plus 4 is 30. Plus 3 more is 33. 35. 36. So look at this. The sum of all possible probabilities is 36, 36. Well, that is 1. That's 1. And that's an important part, is the sum of all probabilities. The sum of all possible probabilities, of a probability experiment is always 1. And in math, if we say always, what that means is always, not most of the time, it means always. And that brings me to our closing observation, and one I've kind of hinted at today. And that is that we say this. The probability of some event, any event E, the very most it can be is 1. And if it's 1, that means it's happening, or it's going to happen. And the lowest it can be is 0. 0 just means there's no way that probability could happen. So all probabilities are between 0 and 1, and the sum of all the probabilities is equal to 1. And if we're studying probability, what you might realize is, wow, that means we are going to spend much of this semester just talking about numbers between 0 and 1. And the last piece, I almost forgot. The last piece was this. Remember what we opened with? Remember? We said that the limiting value of flipping a coin from looking at the work of carriage is 0.5067. 0.5067, that's pretty close to a half. Well, if we want the probability of a head when we flip a coin, well, the number of desired outcomes, well, when you flip a coin, only two things can happen, either a head or a tail. So the number of desired outcomes is 1. The total number of outcomes is 2. And that is how our model supports our observation. So the probability of a head is in fact 0.5. Thanks for watching.